This is 6.1. We're starting Chapter 6, solving one-step linear inequalities. First of all, we have to deal with some inequalities. Inequalities come from statements like the ones listed here, all real numbers less than 2. If I was going to write that with an inequality, I would write it as x is less than 2. Notice that it is strictly less than, not equal to, just less than 2. If I'm going to graph it, I would graph it like this. I would put arrows on both sides, and the most important number I need to worry about is 2. This would be an open circle graph. Open circle because it's not allowed to touch 2, just allowed to get super close to 2. And then the x is smaller than 2, and so I'm going to go smaller than 2. Your graph is the line, that's x. All the x's are the arrow there. And so x is smaller than 2, I have to go to the left of 2. Let's look at another one. All real numbers greater than negative 2. So I have x is greater than negative 2. Notice it's greater than only. If I was going to graph that, the most important point on this line is negative 2. And I would have an open circle again, because I'm not allowed to touch negative 2, but I can get as close to it as I need to. And notice here that x is larger than negative 2. That's what that open mouth on the inequality is, larger. And so my graph, my arrow, needs to be larger than negative 2. Let's look at our next example. All real numbers less than or equal to 1. X is all real numbers. Less than, but it says or equal to 1. If I'm going to graph it, 1 is the number I need to worry about. And I need all real numbers less than or equal to. That means a closed circle. If it's equal to, that means I can hit negative 1. And so I'm going to fill that circle in saying I'm going to go to negative 1. But then x is on the small side, so x is smaller than 1. And so my arrow is going to go smaller than 1 to the left. The last one is all real numbers greater than or equal to 0. X is greater than or equal to 0. When I graph it, 0 is my most important number. I'm going to have a closed circle because it's allowed to be 0. And I need to go greater than. That means x is larger than 0. So we're going to do some manipulations with inequalities. Now remember all your rules from equals, and they transfer to inequality. So let's look at our first example, A. X plus 5 is greater than or equal to 3. Now on the side here, I'm going to do the equation x plus 5 equals 3. Now, inequalities work just like equal sign. If you add something to both sides of the inequality, it's still that the one side is greater than the other side. If you subtract, you still have the same result. So when I solve these side by side, I'm going to subtract 5, and I have x is greater than or equal to negative 2. On this one, I subtract 5, and I have x is equal to negative 2. The way these would be written are a little bit different. If I made a graph, and this was negative 2, on this one I made a graph, and this was negative 2. On the inequality side, I would have to have a closed circle. And remember, we have a closed circle anytime we have this line under the inequality. That means if the x is allowed to be negative 2. Then x is on the large side, and so we graph to the right. On the equals side, when I have an equality, what that means is it's just this point. And that's it. There's no arrows or anything. The answer is negative 2. But you see that the work has been exactly the same. The only difference is what are the answers. In the inequality side, this says that any number that's negative 2 or larger is going to work. That means negative 1, 0, 15, 37, it'll work. On the equality, there's only one answer, negative 2, and nothing else is working. All right, let's look at B. Negative 2 is greater than n minus 4. In this one, I'm just going to solve this as an inequality. I'm not going to show you the equals, but we do the same thing, plus 4, and the 4 is stronger, so it's going to be positive, and 4 minus 2 is 2, is greater than n. We graph it. 2. It's going to be an open circle because there's no line under this inequality, and it's going to graph to the left because n is smaller than 2, or 2 is larger than n. So I'm going to have n be graphed below 2, and that's right here, the arrow's going left. That means any answer smaller than 2 will be a solution to this inequality. Let's look at an example, C. If I gave you a over 3 is less than or equal to 12. Here we have to be careful. I'm going to do another example right next to it, a over negative 3 is less than or equal to 12. To solve this, I'm going to multiply by 3 over 1, multiply by 3, these cancel, and I get a is greater than or less than or equal to 36. However, on the other one, when I multiply, I have to multiply by negative 3, and that changes everything. When you multiply by a negative number on both sides of an equation, you have to change the inequality. It flips to the other side. So this cancels, and you have a is greater than or equal to negative 36. Notice the side by side. When I have multiplication by a positive number on both sides, nothing happens and the inequality stays the same top to bottom. However, when I multiplied by negative 3 on both sides, it changed, and now my less than or equal to becomes a greater than or equal to. Let's go ahead and graph both of these. 36 would be the most important number on this, and negative 36 would be the most important number on this. We have a closed circle because of the equal to under the inequality, and we have that a is on the small side, and so we graph to the left. On the other graph, it's a closed circle because of the equal to, but a is on the large side, and so now I need to graph to the right of the inequality. And that's how you deal with multiplying on both sides of an inequality. Now, when we divide on both sides of the inequality, things change up a bit. Let's look at this next example. D. I'm going to do another side by side. Negative 2b is less than or equal to negative 8, and 2b is less than or equal to negative 8. On the left side, I will divide by negative 2, divide by negative 2. Stop right there. Think about this. I divided by a negative number, which is the same thing as multiplying by a negative number, and so I need to flip my inequality the other way around. Because of this negative 2 and this negative 2, I divided by a negative on both sides. I have to flip my inequality. This becomes b is greater than or equal to positive 4. When I graph it, it's at 4. I have a closed circle, and b is on the large side, the open mouth, and so I graph to the right, saying it's larger than 4. Let's look at the inequality on the right. Again, I'm going to divide, but I need you to notice something. I divided by a positive number on both sides. This negative 8 has nothing to do with flipping the inequality. It was there originally. The negative 8 has no effect. What changes things is what you divide by. I divided by 2 on both sides, and so I don't flip the inequality. I divided by a positive number. When I continue, I get b is less than or equal to negative 4. I'm going to graph that. Negative 4. And I'm going to graph it with a closed circle. And I have b is smaller than the closed mouth side, negative 4, and a graph to the left. Alright, that should do it for this section. Just remember, if you add or subtract, don't do anything to the inequality. However, if you multiply or divide, if it's positive, don't do anything. If it's negative, you have to flip the inequality the other way around to make it work. This is 6.2, solving multi-step linear inequalities. Really, there's not much to show you here. We've gone over the rules for addition, subtraction, multiplication, and division. The only thing I have to remind you of is you need to flip the inequality if you have a negative that you divide or multiply by. So, our first example, A, 2y minus 5 is less than 7. I'm going to solve this just like I would a normal equation. Plus 5, plus 5. I don't flip inequalities with addition or subtraction. 2y is less than 12. Now I'm going to divide by a positive 2. No reason to flip the inequality. Y is less than 12, or 6. We graph it. 6 is my important number. I have an open circle because there is no line under the inequality. And I know that y is on the small side, the pointy side, and so it's smaller than 6, which means I go to the left, and I'm done. Let's look at another example, B. 5 minus x is greater than 4. Now we need to be careful. I'm going to subtract 5 from both sides. Nothing changes. I have negative x is greater than negative 1. Remember, add the opposite and you subtract, you get negative 1. Here we need to remember that the number in front of x is a 1. Now, we've taken the opposite and it's really simple, but when you work on these problems, you have to think about how it is. How do I get rid of negative 1 that's multiplied times x? I divide by negative 1 on both sides. Well, now I'm dividing by a negative number, which means my inequality is going to be flipped. This cancels, I get x is less than positive 1, because negative 1 divided by negative 1 is positive 1. We graph it, we have 1. Notice there's no equal sign, so it's open circle, and notice x is smaller than 1, and so open circle, graph to the left. Let's do one more example, and then you'll be able to do your work. C. 2x minus 4 is greater than or equal to 4x minus 1. So we're going to solve these. We're going to say subtract 2x from both sides. We're getting the variables together. This cancels. You get negative 4 is greater than or equal to 2x minus 1. Notice I didn't divide or multiply, I subtracted, and so I don't flip my inequality. Now I'm going to add 1, add 1. Negative 3 is greater than or equal to 2x. Divide by positive 2, so I'm not going to flip my inequality. Cancels, and negative 3 halves is equal to, not equal to, but is greater than or equal to x. When I graph it, negative 3 halves is my most important point, and I'm going to put a closed circle because of the equal sign underneath the inequality, and I'm going to say that x is smaller than because it's on the small side. This is 6.3, solving compound inequalities. Compound inequalities are just two inequalities that have been pushed together. For example, when we look at A, here's my number line. Now there's two things I need to worry about here in A. The first one is 0, and the second one is 4. Notice that x is in between them. What this is saying is x is between 0 and 4. Notice that x can touch 4, it can go all the way to 4, but it cannot go to 0. So let's put our important points on here. 0 and 4. I'm going to do an open circle on 0 because I can't go to 0, and a closed circle on 4 because I can. Then I just need to put a line in between them saying that these are connected. On this other one, this is a compound inequality, B. Notice that x is not between them. When you have an OR compound inequality, and that comes from the word OR, either this is happening or this is happening. But we're going to graph it pretty much the same way. We're going to put negative 1 and we're going to put 2. Remember, you need to put them in numerical order. I'm going to have open circles on both of them, but I have x is smaller than negative 1 and I have x is larger than 2. So I'm going to graph on the outsides. You'll be doing a lot of this type of graphing, but there's also opportunities where we're going to need to solve for x. Example C is a compound inequality, an AND compound inequality, where 3x minus 8 is larger than negative 2 but less than 10. Now I don't know what x is, and so I'm not going to be able to graph this. Once I have x alone, I can graph it. Now, what you could do is separate this into two inequalities. This would be negative 2 is less than or equal to 3x minus 8 and 3x minus 8 is less than or equal to 10. This would be a perfectly fine way to solve it. You'd solve each one by themselves and you would have a correct answer that you could graph. However, there's a faster way to do this type of a problem. I'm going to rewrite the problem here, and I'm going to solve everything by itself, or as one inequality. The way we do this is the same as you would for any other inequality. We start where the x is, and I need to get rid of that constant 8. So I'm going to add 8. And we have to realize this is two inequalities. So I'm going to add 8 over here, but I'm also going to add 8 over here. This becomes 6 is less than or equal to 3x, because these cancel, which is less than or equal to 18. And now I'm going to finish this off by dividing by 3 over here, here, but also over here. I get 2 is less than or equal to x, which is less than or equal to 6. We can now graph it. I have 2, I have 6. I'm going to have two closed circles and a line in between, and you're done. Now this is another example of an AND graph, but there's a little bit of a trick to it in one of the steps. Now I'm going to solve it like I would normally. I'm going to add 2, because that's a negative 2, to all three of these areas. and I get 0 is less than negative x, don't forget that negative, which is less than 3. Now I can't finish this as is. I need to realize that's a negative 1, so I'm going to divide by negative 1 on all 3 areas. And we need to remember from the last section, whenever you divide by a negative number, you have to flip the inequality. And so now this becomes 0 is greater than x, which is greater than negative 3. And so in reality, if I was going to write this, I'd write negative 3 is less than x, which is less than 0, just so I can graph it without worrying too much about my order. I need open circles on both and a line in between. Now I'm not going to be graphing the OR inequalities. You can do the OR inequalities. It's just solving two separate inequalities side by side. It's not really a huge deal. Anyway, good luck. One thing that you will have to watch out for is finding if something's a solution or not. And here's how you'll do it. I'll just put a little note on the side here. Is 7 a solution? And so I'll take the original, negative 2 is less than negative 2 minus x, which is less than 1, and I'll fill in a 7 for x. So negative 2 is less than negative 2 minus 7, which is less than 1. Negative 2 is less than negative 9, which is less than 1. Now, if we look at it, this inequality is correct. Negative 9 is less than 1. However, this one's not. Negative 9 is not greater than negative 1. It's smaller than. And so we know that 7 is not a solution to this inequality. And that would make sense too, because we found out earlier that x has to be between negative 3 and 0. Or in this area, 7 is not even close to that area. Alright, good luck. Alright, we're looking at 6.4, solving absolute value equations and inequalities. 6.4 is different than most of the stuff we've been doing. We studied absolute values, but we've never studied them in equations. The important thing to remember is that if I'm solving an inequality, or not an inequality, but an absolute value, I have to remember what it means. Off to the side here, I'm going to show you something. Now, if I have the absolute value of something equals 5, well, what could that something be? What could this inside there be? Well, I'm going to give you a selection of some numbers here. I could have 5. I could have negative 5. If I put 5 in, I get the absolute value of 5 equals 5, or 5 equals 5, and that checks, it's true. However, when I put negative 5 and I get the absolute value of negative 5 equals 5, and then I get 5 equals 5, and this is also true. And this is what makes absolute values a little bit more difficult than your average equation. You have to account for both answers. In order to get rid of this absolute value in the equation that we're going to solve, I need to account for the 5 and the negative 5. And so I'm going to get rid of the absolute values by doing this. X minus 2 could equal 5. You just copy down what the original equation is. But then you have to write a note. But that's not all it could be. It could also be that x minus 2 would equal negative 5. If you don't include that negative, you will not solve it correctly. But now it's easy. You just solve 2 plus 2 plus 2. X is equal to 7. Plus 2 plus 2. X is equal to negative 3. And there are my two solutions. Couple of things to watch out for. When you're solving inequalities, you want to make sure that you have the absolute value by itself before you move. So let's make this our first real example, A. If I gave you the absolute value of 2x minus 7 minus 5 equals 4. I want to get that absolute value by itself. That means I need to get rid of the 5 by adding 5 to both sides before I do anything else. The absolute value of 2x minus 7 is equal to 9. Now I can use my absolute value rule. To get rid of the absolute value, I have to say that 2x minus 7 could equal 9, but I also have to include that 2x minus 7 could also be equal to negative 9. If you don't include that, you will be wrong. Plus 7, 2x is equal to 16, divide by 2, x is equal to 8. On the other side, plus 7, 2x is equal to negative 2. Don't forget that's a negative there. Divide by 2, x is equal to negative 1. There are a couple of little details that you have to watch out for when you have equations with absolute values. The first one is if I have the absolute value of x plus 3 is equal to 0. Then when I make positive and negative, I have x plus 3 is equal to positive 0, but there is no positive 0. And there is no negative 0. So in this one case, you are going to get one answer. The other thing you have to watch out for is this, the absolute value of x minus 4 plus 7 is equal to 3. So I would subtract 7, and I would say the absolute value of x minus 4 is equal to negative 4. Now you have to stop there. Think about it for a minute. This is an absolute value. And what do absolute values do to a problem? They always make it positive. So will your absolute value ever equal a negative number? No. And so this is no solution. As soon as you have an absolute value all by itself equal to a negative number, you have to stop and say, this has no solution, I can't continue on. Next example, we're going to start our inequalities with absolute values. Inequalities are a bit different in that we have to account for both solutions and we have to flip our inequalities accordingly. Here's some rules for inequalities. When you have a absolute value is less than some number, you're going to make an AND statement, and you're going to have to solve them as an inequality with the same thing less than the number and also greater than the opposite of the number. When you have a greater than, the absolute value is greater than a number, then you're going to say that what was in the absolute value is greater than C, or, notice the word or, the number will be less than the opposite of C. Let's do two examples of those to show you what it is. Alright, the first example in absolute value inequalities. If I gave you the absolute value of x minus 4 is less than 3, then I need to remember that this is going to be an AND graph. This right here, less than, makes this AND. So, we change it to x minus 4 is less than 3. You just copy it, and you put the word and. X minus 4, you flip the inequality, is greater than negative 3. Make that negative. You're going to solve both of these, and it's going to work out really nicely. Plus 4, x is less than 7. Plus 4, x is greater than 1. And so when we graph this, we would graph both of them. What you could say is that 1 is less than x, which is less than 7. And I'd graph 1 and 7. I'd have open circles on both, and I would say they're in between. And graphs are in between. Our second example B. If I gave you 2x plus 1 minus 3 is greater than or equal to 6. Remember that absolute values need to be alone before you start using their rules. And so I'm going to add 3, add 3. The absolute value of 2x plus 1 is greater than or equal to 9. Now I'm going to use my absolute value rules. The first thing I'm going to do is I'm just going to copy it straight. I'm not going to change it in any way right now. So 2x plus 1 is greater than or equal to 9. There we have it, but now we need to put the or. Because I have a greater than, this is going to be an or graph. Check your book if you get confused. It's on the page 354, and you'll be able to see what's an and an or. Then I write 2x plus 1. I flip the inequality is less than or equal to, and I make it negative 9. But then we just solve like normal. Minus 1, 2x is greater than or equal to 8. Divide by 2, x is greater than or equal to 4. Minus 1, add the opposite on the second side. 2x is less than or equal to negative 10. Divide by 2, x is less than or equal to negative 5. This is an or. When I make my number line, I have negative 5. Remember, that's smaller than 4. And 4. I'm going to have closed circles on both. And I'm going to graph on the outsides. Alright, that should give you pretty much everything you need to know about absolute values. Good luck. On second thought, let's go ahead with one more thing. What you have to watch out for with absolute values is this. If I gave you that the absolute value of 2x plus 3 is greater than negative 5, you actually don't have to do any work. Because absolute values are always positive, and positive numbers are always bigger than negative numbers. And so you can say all real numbers. That means any number you want to pick will work because the absolute value will make it positive and you don't have to worry about it. Likewise, if you have the absolute value of 2x plus 3 is less than negative 5, well, absolute values are positive. They can't be less than negative numbers. And so you have to say no solution. So watch out for those two. They will not work. Alright, we're going to be graphing linear inequalities in two variables. When we look at this, the best way I think to do this is to consider just examples. So I'm going to be graphing a few different linear inequalities, and you're going to be seeing the results of that. The first one we're going to be doing, A, will be 2x minus 3y is greater than or equal to negative 2. In order to graph this, I need to put this in slope-intercept form, so I'm going to solve for y minus 2x minus 2x. Negative 3y is greater than or equal to negative 2x minus 2. I'm going to divide by negative 3, divide by negative 3, divide by negative 3. I get y is greater than or equal to 2/3 x plus 2/3. So what I'm going to do is graph it. I'm going to go to 2/3 on the y-axis and graph my y-intercept. Then I'm going to go up 2, 1, 2 over 3, 1, 2, 3. I'm going to connect my dots in a line. Now comes the tricky part. Here's what I do to remember this. I say whatever y is it larger than or smaller than? Well, in this case, y is larger than the rest of the equation. And so, I'm going to graph above the line. If we look at it, there's two sides of this line. There's a top and there's a bottom. And so I'm going to graph above this line. That means everything above this line gets shaded in. That means half the plane is shaded in. You don't go below the line, and you can touch the line. The reason you can touch the line is because of this equal part right here. And so this is a solid line, and you are done graphing. Let's look at another example. This is B. In B, I'm going to use x plus y is greater than 3. I'm going to solve again for y by subtracting x, and I get y is greater than negative x plus 3. Now I'm going to graph it. Remember that the slope is negative 1 over 1. And so I go up to 3, graph the y-intercept, then I go down 1 over 1 to do the slope, and I connect the dots. Hopefully you connect the dots better than I did. Let's try that again. A little bit better. And we need to figure out, is it above the line or below the line? But before I can do that, I have to watch out for one thing. You see that greater than with no equal sign underneath? That means we're not allowed to touch the line. Similar to when we had an open circle when we graphed on a number line. So how we show that is to have a dotted line. So this line is going to be dotted, and what I'm doing, I'm just really taking an eraser and erasing so it makes it dotted. So it shows that there's gaps in between there. And what that is telling us is you can get as close to the line as you want to, but you can never touch that line. Now I graph it. This says I need y to be larger than the line, and so I'm graphing above it. If the inequality was flipped, we would graph below it. There we go. The only other thing that you really need to watch out for is to see if, well, you just need to see vertical and horizontal lines. So, see, x is less than negative 2. D, y is less than or equal to 1. So I'm going to make really quick graphs right here. And we need to remember that when we're graphing an x, this is negative 2. notice this is a less than, and so I'm going to make a dotted line on negative 2 straight up and down. Okay, now I just need to know, am I going to graph on the left or am I going to graph on the right? Well, if x is less than negative 2, then you're going to shade in the numbers less than negative 2, right over here. If it was greater than, you would hit the other side up. When I'm graphing a y, remember this is y is 1. There's 1 right there. So it's going to be a horizontal line on 1, but this is a solid line. Notice that I have an equal to right here, and so I'm just going to draw it at 1 straight through. Let's try that again. There we go. And now it says that y is smaller than 1, so I'm going to shade in everything smaller than 1. And there you have it. You will have a few problems that will ask you this. Alright, you're going to have to do a problem just like this. Is the ordered pair a solution to the inequality? So we have 2x minus 3y is greater than or equal to negative 2. The point is 0, 1. We're going to fill in 2 times 0 minus 3 times 1 is greater than or equal to negative 2. 0 minus 3 is greater than or equal to negative 2, or negative 3 is greater than or equal to negative 2. Now when we think about it, is negative 3 greater than negative 2? No, it's not. It's smaller. Is negative 3 equal to negative 2? No, it's not. They're not the same number. And so our answer is no. This point is not a solution to this inequality. If it works out, the answer would be yes. Good luck.